So I said, push on the lab table. Do you feel like you're working hard? And you all did. You were exerting effort. You were, there was force. But you've done sum of forces diagrams. What was true of that force that you were exerting on the lab table? What was happening? Huh? Well, it wasn't moving, which means from a force perspective, if you had to draw a free body diagram of that, what would that look like? It's balanced. It's an equilibrium. Sum of forces equals 0 on whatever axes you're pushing on, meaning, depending on what direction you were pushing, either the normal force being exerted back is equal to the force you're exerting, or just the reaction force from the table is the same as the force you're exerting. Nothing's moving. So that's what we did in the last chapter, was all that sort of balancing forces. Well, now we're going to talk about work. And when I said you didn't do a single lick of work, that's because work is only done in a science sense and a physics sense if the thing moves. If you can move the object, you've done work on it. And we talk about object A doing work on object B having work done on it. It's a different use of the word than in just general English. So be careful. But yeah, in physics, if the object doesn't move, if there's no displacement, then there's no work. Period. How many of you have done any calculations with work as freshmen? Do we do that in physical science anymore? They changed all the standards since the last time I taught physical science, so no? We used to do it, but I don't think we do anymore. Because if you had, you probably would remember this. Work equals force times distance. That's the simplified version that we usually use, or we used to use with freshman physical science, because they haven't done vectors yet. They haven't looked at, they're only looking at a single dimensional motion. And of course we have multiple dimensions to motion, because we know how to do vector analysis. Well, what that means is that we have to consider the vectors of the force. You know that force is a vector, and so you know that there can be, some of you, a couple of you were pushing down like this on the lab table. Is all your force on either axis? No, not unless you tilt the axis. Your force is distributed across the x and the y axis. So a lot of times forces are. You've just spent a whole chapter doing that. You know that. The work is only being done by part of the force. When you drag little boxes around the hallways, a lot of you, and I think only 2 or 3 people came up with, what I consider to be like the perfect answer on the lab, which is, why does the amount of force needed change as you increase the angle? Well, because more and more and more of that force is essentially being wasted. It's not doing anything to actually move the object. It's now just fighting gravity. So great, you're reducing gravity, but you're not actually using that force to move the object. When you're attempting to move an object by exerting a force on it, what this tells you is the more of the force you can get on the same plane as you want the motion to occur, the better. If you've ever pushed a car out of mud or snow, it's the same idea. You want as much of the force as possible to be on the plane that the object is going to move on, or that you want it to move on. Because of that, only part of the force that's being exerted on the object is actually doing the work. This is a really important distinction. If you're exerting 100 newtons of force on something, but only 10 newtons of that force is on the plane of motion, then only 10 newtons of force is doing the work. That means that the sort of more complicated, stepped up equation for work is that work is equal to force distance times cosine theta, where theta is the angle between the applied force and the plane of the motion. Now, I'm going to tell you this. Your textbook gives it as work equals FD cosine theta. State standards give it that way. I just don't trust authority. That's my whole problem. I know this. I still always double check to make sure that depending on, well, okay, here's the catch. Here's the catch. Because it depends on, well, yeah, it does. Depends on how you line up that vector. If you were to line it up as this, then it would be sine if you were using that angle. So just be careful. Make sure that that cosine theta really, and look at your picture. You're still going to have to draw a free body diagram for all of these. Yay! You were so sad because you thought you wouldn't have to draw those anymore. I know, aren't you relieved now? When you draw that free body diagram, that visual representation gives you a way to visually align the plane on which the motion is happening and the angle between the force and the motion. So my takeaway from that is, I don't trust authority. I know it should always be cosine theta, but make sure that you've got your forces and vectors lined up so that it is cosine theta. Network. Ha 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 ha. Anyway, just like you found net force, you can find network, because most objects at most times have a whole bunch of forces acting on them. And the one that's doing, well, and this is just like, you know that it's accelerating along the vector of the net force. Well, the work is being done along the vector of the net force, because, of course, that work is being done when acceleration is happening. Well, actually, no, it doesn't have to be, because it could be at constant velocity. It would still be having work done on it. But it's still going to, the work is still going to happen on the axis of the net force. Okay. Which means we beef up the equation one more time and we say that the net work being done on the object is equal to the net force times the distance, or the displacement, times cosine theta. Which means you still have to know how to do sum of forces. You still have to take a bunch of forces and resolve them into a net. Questions? We'll go through the sample problem on page 169. Grab a book. Got to clear all the chem crap. Okay, so I've started off with a free body diagram, and the problem reads as follows. How much work is done on a vacuum cleaner pulled 3 meters by a force of 50 newtons at an angle of 30 degrees above the horizontal? I've done a free body diagram. I'm going to list my variables. So the force is equal to 50 newtons, theta equals 30 degrees, displacement is equal to 3.00 meters. I want to introduce you to one new symbol. Why is it important? It's important because if you go on to take another physics class, well, okay, it's important because it helps keep your brain straight. It helps keep you sorted. But it's also important because if you go on to another physics class or you're creating something that you're going to have to share with somebody else doing science, they'll throw things at you. This is a free body diagram. Remember that all forces originate from the center of the object. Forces do not originate outside the object. Forces are not labeled above the object. They start at the center of the object. They go in the direction they're going. Period. That's basic. Okay. That's a line for motion. Note that it's not touching the object. We'll wrap it up next week.